Okay, thank you. So first of all, I'd like to thank the organizers for inviting me to speak here. I also apologize that this talk will not do justice to the title of this conference or of this gathering, because while there will be some gravitational waves in this talk, okay, there will be nothing beyond the standard model. But perhaps the hope is that maybe someone will apply these results to the standard model someday, to beyond standard model physics someday. So this is the title of my talk, Gravitational Wave Tales from Soft Theorem. So I'll begin by describing the kind of questions that we'll try to address in this talk. So let's imagine that there is some violent explosion in space where some stationary system breaks apart into fragments. This process will emit gravitational wave, okay, because any moving or accelerating mass does emit gravitational waves. And if we have some detector D that's placed far away from this source, from where this event takes place, okay, it will detect this wave as some kind of ripples in space-time. And one example of such kind of violent explosion is the supernova explosion in space. Now one can consider a more general situation, okay, where instead of a single object breaking apart into fragments, okay, we have collision, okay, where a set of objects come together, interact, and then they fly apart. And during this process, they may exchange mass, energy, momentum, and various other quantum numbers. So this will also produce gravitational waves. And here again there is an example of such collision in the sky, okay, bullet cluster. So the bullet cluster refers to a supercluster of galaxies that pass through another supercluster of galaxies. Each of these superclusters weigh about 10 to the 14 times the mass of the Sun, and they pass at a relative speed of about 1% of the speed of light. So this will produce some gravitational waves, and we would like to study those. Now in general, if you want to compute gravitational waves produced during such processes, it's a complicated exercise, and it's complicated because of two reasons. First of all, when the objects are close, then they may undergo complicated non-gravitational interactions, as in the case of explosion of supernova, for example. There the nuclear forces play an important role in the whole mechanism of the explosion, and those are complicated to understand. Now, even when such complications are absent, there is a second complication, and that is that gravity is described by nonlinear partial differential equations. So even if the interactions were purely gravitational, okay, for example in the case of black hole merger, the analysis will be complicated because of the nonlinearity of gravity. Now surprisingly, it turns out that some results in quantum theory of gravity, which are known as soft graviton theorem, these results can be used to get analytical results on some aspects of classical gravitational wave. And this is what I'll try to describe in this talk. Okay, what aspect of gravitational waves can be studied by the soft graviton theorems, and what kind of results do we get from applying these theorems. So here is a list of my collaborators in this project. So Alok is a faculty member at CMI, Vishwajit and Arnav are postdoctoral fellows in various places, and Debanjan and Babli are graduate students, and they did some work on this in their semester project. And I should also add that during the recent years, most of the recent progress in this field has essentially been pushed by Vishwajit. Okay, so he is in fact part of almost every development that has taken place in this field. Okay, so let me begin with an introduction where I'll also try to set up all the conventions. So as you all know, in Einstein's general theory of relativity, a gravitational field is a symmetric 2-index field, which I'll denote by h mu nu, and this measures the distortion of space-time. And this field is sourced by mass or energy. And we'll use the convention where the h mu nu is defined as the difference between the metric and the Minkowski metric eta mu nu, okay, and divided by 2. Okay, that will be my convention for h mu nu. Okay. And the other point I want to mention here is that at least while stating the results, I'll keep all the constants explicit. Okay, I'll not set, for example, c equal to 1 or h bar equal to 1. Okay, so everything that appears that is there in the formula will be there explicitly in display. So gravitational waves involve time and space varying h mu nu. And the key feature that distinguishes gravitational radiation from other kinds of gravitational effects, okay, like for example the static gravitational field of a source, is that at a distance r from the source, the fields fall off as 1 over r and not as 1 over r square or faster. Okay. And here when I say fields fall off as 1 over r, that means I specifically mean that the observable effects fall off as 1 over r. You may say that, okay, gravitational potential fall off as 1 over r, but that's not observable. So radiation has this specific feature that it falls off slower at larger distance compared to the static effects. So h mu nu, which describes the fluctuation of the metric, can be measured by a gravitational wave detector like LIGO. And the goal of a theorist will be that for a given process, we want to compute h mu nu at a faraway detector, okay, and we'll be focusing on the part that falls off as 1 over r, okay, throwing away terms that fall off as 1 over r squared or faster. But I should have said that if you have any questions, please feel free to stop me in the middle. So here are the conventions, okay, which are all more or less standard. So c will denote the speed of light, capital G will be the Newton's gravitational constant, space-time coordinates will be denoted by x mu with mu running from 0 to 3. And as I said, we will keep the speed of light explicit in our formulae, okay, even though when I do the explicit analysis, I may set c equal to 1. So x naught will be c times t, okay, where t is the usual time coordinate, vector x is just the 3 components of the space coordinates. Similarly, the 4 momentum p mu will have a 0 component, which is energy divided by c, and then these are the usual momenta of objects. My convention for the Minkowski metric will be mostly plus signature, okay, so it will be diagonal matrix with -1, 1 minus 1 eigenvalue and rest plus 1 eigenvalue. So the dot product between 2 vectors, for example, will be given by this. And in this convention, p square, which is p dot p, is minus m square c square. Okay, so this, first of all, you get p0 is E over c, right? And then using the usual relation between energy and momentum for a massive particle, we can show that this is minus m square c square. Okay, again, these are all standard, but sometimes one uses somehow different sign conventions, so I am giving these things explicitly. We will be using summation convention, and throughout this talk, whenever I talk about, whenever I raise or lower indices, it will be understood that that's all done with flat Minkowski metric. Okay, we will never raise and lower indices with the full metric. Okay. I'll write things out explicitly if I am using the full metric. So upper index and lower index are simply related by multiplication by the Minkowski metric. So in particular, we'll have relations of this kind. Are there any questions on the conventions? Okay, so now I'll try to first give a summary of the results. Okay, what we know so far. Okay. in this field. What can we say based on soft graviton theorem? And then later I'll try to discuss how we arrive at those results. Okay. So as I had said earlier, the specific problem that we will be considering is that of scattering in space. Scattering is more general than explosion, right? So once I give the result for scattering, you can also read out the result for the explosion, okay, even though I'll give it separately later. So the situation that we'll be considering is that a set of objects which carry 4 momentum p1 prime to pm prime, they come together, interact, and then they disperse as a set of objects with 4 momenta p1 to pn. We make no claim about the relationship between the number of particles that are there in the past to number of particles that are there in the future, right? Because they can fuse and decay, they fuse and split in that process. The only constant that you have to impose, of course, is the momentum conservation, right? The total sum of what p1 prime to p2 pm prime should be equal to sum of p1 to pn. So a scattering events like this, okay, has to be described by using some space-time coordinate, and I'll choose the convention that the space-time coordinate in which you will be describing the scattering is such that the origin of space-time is somewhere inside the region where the scattering event is taking place. Right? A set of objects are coming together and dispersing, and again the precise choice of the origin will be irrelevant for what we are going to discuss. Now imagine that there is a detector placed somewhere far away. So this is going to emit gravitational wave, and that wave is going to reach the detector at some later time. So we label by t0 the time at which the peak of the signal reaches the detector. Okay, so t0 will be given by r over c, that's the light travel time, okay, in flat space. But because you are talking about gravitational physics, there are corrections to this. Okay, in fact, there is a correction proportional to log r, and these corrections come because there is gravitational drag on the gravitational wave. Right? So once you produce a gravitational wave, it doesn't propagate in flat space-time, but it propagates in curved space-time, and that curving of space-time also gives some correction to this, the time at which this signal reaches the detector. Again, the details of what T0 is not going to be important, okay, because when I say that the peak of the detector reaches at some time T0, right, it need not be exactly the peak, because time of order 1, an error in T0 of order 1 will not be relevant for the results that we are going to describe. Okay, so T0 is roughly the time at which the bulk of the signal reaches the detector. So we'll define retarded time at the detector u as t minus t0. So the detector is sitting far away receiving signal. The bulk of the signal reaches the detector at certain time t0, and we define u as the time measured by the detector relative to the time t0 where the bulk of the signal reaches it. And the part of the gravitational wave form that we are going to focus on will be the late and early time tail of the wave, which means that the value of h mu nu at the detector at large positive u and large negative u. Now we are doing this not because this is the only important thing that we should study, but this is the quantity for which you can say something. Okay, we can say something analytically without having to go through numerical analysis, and I'll describe later what we can say about this waveform. So you want to study h mu nu as a function of u for large positive u and large negative u. It turns out that the various formulae that I am going to show you are slightly easier to write in terms of this different quantity e mu nu, This is sometimes called the trace reverse gravitational field. So E mu nu is related to H mu nu by this simple formula over here. So you basically subtract out a part proportional to eta mu nu, where the proportionality constant is a trace of H. So what I am going to do is to give you the formula for E mu nu at large positive U and large negative U. But this doesn't really, we don't lose out anything by doing this, because we can reconstruct H mu nu from E mu nu. Right? Given this relation, we can just take the trace on both sides to relate trace of E to trace of H, and then substitute it here to write H mu nu in terms of E mu nu. So if I give you the result for E mu nu, that's as good as giving the result for H mu nu. Now the first result is that if we look at the term proportional to R inverse, and that's what we will do, as I said, because radiation falls off as 1 over R. Okay, so that all the static effects are gone. Okay, we don't care about terms that are of order R to the minus 2 or higher powers of R inverse. So terms proportional to R inverse have the U dependence of this form. So for large negative U, E mu nu has a piece that goes as 1 over U times a constant. Then it has a piece U to the minus 2 times log of mod U times another constant G mu nu. And then there are corrections of order U to the minus 2. For large positive U, E mu nu has a constant piece which I will call A mu nu. Then there is a piece proportional to U inverse whose coefficient I will call B mu nu. And then there is a piece proportional to U to the minus 2 log U, and the coefficient I am going to call F mu nu. Okay, and again there are corrections of this kind. Okay. Now you notice that we have an ambiguity in defining U, right? As I said, because T naught we don't know exactly what it is, right? Because you have not defined what T naught is precisely. It's some time at which the peak of the signal reaches the detector. So if we make a shift of T naught of order unity, that shifts U by a term of order 1. If you shift U by a term of order 1 here, then you can, for large U, you can expand it out in a Taylor series expansion in 1 over U, and you can easily convince yourself that shifting U by a term of order 1 doesn't affect these coefficients over here. Right? So these coefficients are unambiguously defined for large U, even if U is ambiguous up to shifts of order 1. So for example, if we shift U by order 1 here, right, and you can expand this in powers of 1 over U, so there will be 1 over U term, and then the next term will be of order 1 over U square. Okay. But 1 over U square is small compared to this one for large positive U. Okay. So this coefficient is not going to be affected by the ambiguity in choosing the origin of U in this term. Okay, so this is the general structure. But now the important point is that these coefficients over here can be shown to be given solely by the 4 momenta of the ingoing and outgoing objects without requiring any knowledge of the details of the scattering process. So if somebody gave you what particles went in and what particles went out, in the middle they can interact via nuclear explosion, right, or some unknown interactions. It doesn't matter. As long as you know the incoming momenta of particles and the outgoing momenta of particles, these coefficients can be completely fixed. Is this statement clear? Are there questions on this? Yeah. Yes, it is true for inelastic scattering. They can fuse and then disperse. It's completely general.
This T0, supposing you take that as just R by C, the distance.
Yes.
Then this is just the retarded time, and normally it is positive because of causality.
Yes.
You are saying it can be negative because of the gravitational drag. How can it be negative?
No, it's not. It cannot be negative, right? But see, there is a log R piece also, right? Log R, yeah, because it's not R over C, right? I'm saying that, okay, let's have a detector there, right? The detector is observing some signal comes here. Right? I'm saying T0 is the time at which the peak of the wave reaches the detector, right? Suppose there are two peaks, right? Then how do you determine what T0 is?
Determine in terms of R.
R plus order 1.
Yeah, order 1.
Yeah, R plus log R plus order 1, right? So, all I'm saying, the order 1 error that you might make in defining T0, okay, doesn't affect this formula, right? Because order 1 error in T0 will translate to order 1 uncertainty in U, right? But that you can expand out for large U, and these coefficients are not affected by such ambiguity.
Negative U. What does the negative U? That it is violating causality because of the gravitational wave track?
No, not really. Negative U may basically, so you are asking how come there is a signal
is reaching before
the peak reaches. Yeah.
No, the distance. Suppose we have defined that T0 just as the distance.
Yes.
And this T has to be larger than R by C.
The point is when the two objects are coming together, right? They start interacting far before they actually meet, right? Because there is a long range gravitational force that is operating between them.
So there is no sharp T.
There is no sharp T, yeah. Right? So that's why you can also see the signal before the peak of the signal reaches it. Yeah, so you'll see some 1 over U and 1 over U square log U piece before the collision has taken place, and then after the collision has taken place, it will decay as 1 over U and 1 over U square log U. In the middle, there is a very complicated waveform, right? That will not be able to calculate by these soft graviton theorems. Any other question?
What about finite size corrections?
Finite size, yeah. So these objects can be finite size. Yeah, doesn't matter. Yeah. So finite size means there will be higher multiple moments, for example, right? That these are not point-like objects, but again, these coefficients are not affected by that. Okay, so in the next 2 slides, I am going to give you the formula for these coefficients. Now, the formula will look complicated, okay, but the purpose is not to scare you with this formula, okay, but just to convince you that these formulae exist. Right? There is a very concrete formula for all of these coefficients, okay, which you can write down, okay, and then eventually I will try to explain the logic that we use to get this formula. Right? The precise details probably will be given only in tomorrow's lecture, but today at least I will give an outline of the logic that goes behind this formula. Okay, so here are the formulae for A mu nu, B mu nu, and C mu nu. So A mu nu was the coefficient of the constant piece at late time. B mu nu was the coefficient of the 1 over U piece at late time, and C mu nu was the coefficient of the 1 over U piece at early time, okay, for large negative U. R here is the distance to the detector that I have already stated before, and N is a 4 vector whose first component by convention, the 0th component is 1, and whose spatial components is just the direction cosine of the detector. Right? This x vector over r, right, this basically tells you the angle at which you have placed the detector. So you have a set of incoming momentum, a set of outgoing momentum in some coordinate frame, and the detector is placed at in some direction. Right? That direction is captured by this 4 vector n. Okay, first component by definition is just 1, and then the spatial components are the direction cosines. And as I said, the purpose of this formula is not to show you the details, but just to show what it depends on. Okay? And if you examine this formula carefully, you will see that these formulae depend only on the momenta of the incoming and outgoing objects. Okay. And as I have also said that all the explicit constants, even including universal constants like G and C, are in this formula. Yes. Yes.
So these could be the momenta of each of the stars or the clusters themselves?
I think one can think of this as momenta of the clusters themselves. Of the whole cluster, yeah. Right? You can take the P as the momenta of the whole bullet cluster together.
Is that clear that the answer will be the same?
Yeah, the answer will actually be the same because if you just add, suppose you have two particles which are moving parallel, right? Then you can see from this formulae that we can either treat them as one object with momentum p1 plus p2 or two separate objects. They give the same formula. Okay, so it doesn't really matter whether you think of them as a collection of stars, right? As long as they are all moving in the same direction. Right? If they are not moving in the same direction, then of course you have to treat them separately. But inside the bullet cluster, more or less the overall velocity, right, is that they are moving in the same direction. Yes, it is in fact, instructed to apply this formula for the bullet cluster, right? And in fact, you get a strain of about 10 to the minus 14, right? Which is of course far more than what LIGO has detected, right? But the catch is that you cannot just detect the strain by itself. What you detect is the time variation of the strain, right? Or the second time derivative of the strain, and that is much smaller here because the change takes place over millions of years. But this, for example, if you use the corresponding this formula to calculate the gravitational waveform for the bullet cluster, right? What you can say is that this produces an asymmetry in the metric, in the local metric, which is 1 in 10 to the minus 14, right? That's because h mu nu, of course, is directional. Okay, so if there are no other questions on this, we will go to the formula for f and g, right? Which will be, as I said, more complicated, but they depend exactly on the same set of variables. So here are the formulae for the f and g. So this is the coefficient of the 1 over u square log u term, and this is a coefficient. This is in the future, and this is the coefficient of the 1 over u square log of mod u term in the past. And again, you see that even though the formulae are much more complicated, they depend only on the momenta of the incoming and outgoing particles. So you can just evaluate them. Once you know what went in and what went out, you can just evaluate these formulae and find out what kind of tails you have in the gravitational wave radiation. Yes.
Are these the same thing that in South Theorem is written as angular momentum?
Yes, they come from angular momentum. Yeah.
They're just writing in terms of momentum, but it's something.
Exactly. Yeah. Yeah, the point is you derive them from the angular momentum, right? But see, the angular momentum requires not just the momentum but also the relative displacement, right? But the dominant part, right, that contributes to this order is not the relative displacement, but the fact that as things go past each other, there is a logarithmic drag, right? And that's what is the dominant contribution that comes in here. But eventually, you are right that it comes from the angular momentum in the application of the soft theorem. Okay, so these are the formulae. Now, I'm going to describe some specific properties of this formulae. Okay, some features. So here are the two formulae again, right? This is that large positive U, this is that large negative U. So first, look at the memory. This term, a mu nu, which is a constant term. What this is saying is the following: that imagine that we start from some metric where g mu nu is eta mu nu, right? Which means h mu nu is 0. What this is saying is that after the gravitational wave passes the detector, right, at far future, g mu nu doesn't come back to eta mu nu. It comes back to eta mu nu plus this constant a mu nu. This is what is normally called the memory. Okay. It says that if you have a detector like LIGO, okay, and if the mirrors were free, okay, then what would happen is that after the gravitational wave has passed through, the mirrors don't come back to their original position. Right? Imagine that you started by setting up the LIGO detector where there is destructive interference between these two beams. Now, as the gravitational wave is passing through, of course, the destructive interference will not be maintained anymore. It will start oscillating. Okay. But after the gravitational wave has passed through, right, what this mu nu coefficient says that you will not come back to destructive interference, you will come back to some constant phase between the 2 meters, between the 2 beams. So this means that there is a permanent change in the state of the detector after the passage of the gravitational wave. Now LIGO doesn't see this because there is a restoring force that brings the mirrors back to their original position, right? But a space-based experiment like LISA, for example, will see this, right? Because there is nothing that drags back the mirrors to their original position. Okay, so this memory can be, in principle, be seen in the space-based experiments. Now the memory term has been known for a long time, right? In fact, it was known from the 70s by the work of various people. Okay. And in recent years, starting with the work of Strominger and others, okay, this memory was related to the soft graviton theorems. The other coefficients, okay, are what we'll call the tail terms, and these were discovered more recently. In fact, these were discovered through the soft graviton theorem. The universality of this memory of these tail terms were determined through the soft graviton theorem, okay, while memory itself was known earlier, but it was connected to soft graviton theorem more recently. Okay, so this I have already emphasized before, but let me do it again. That these coefficients can be expressed in terms of the moment of the incoming and outgoing objects without knowing what forces operated and how the objects moved during the scattering. And this is a consequence of soft graviton theorem. I'll describe later. At least I'll give an outline of how soft graviton theorem is useful in deriving these results. Now, in contrast, if we are to compute h mu nu at finite time, that will depend on the details of the scattering process. Whether there is a nuclear explosion in the middle or not will affect what h mu nu is at finite time. And this, in general, will involve very complicated calculations, both because there may be unknown interactions that take place when the objects are close together, and there may be nonlinear effects of gravity, right, which are handled here in a way that I'll describe, but not for determining h mu nu at finite time. Now, there is one complication in this formula that I have not emphasized before, but now I'm going to emphasize it. That if we look at the expressions for a mu nu, b mu nu, and f mu nu, these are final states, right? So let me show you these expressions for a mu nu and b mu nu again. A mu nu and b mu nu, and similarly f mu nu is here. Okay, but I think it's enough to just focus on these for illustrating what I'm going to say. So here the sum, these PMU are the final state momenta, these are the initial state momenta. Now when I say that this sum involves the final state momenta, it includes everything that is produced during this process. In particular, if this process produces finite energy gravitational waves, and of course it will in general, then their energy and momentum also must go into this sum. This makes it somewhat inconvenient to use these formulae. C mu nu doesn't have this problem, right? Because you don't expect gravitational waves in the initial stage. In the initial stage, you think of a set of matter coming in, okay? And C mu nu doesn't have any dependence on the final state momentum, okay? But these do have dependence on the final state momentum. So if you want to really use these formulae to compute A and B, what you need to know is the finite energy gravitational waves that are produced during this process, besides the matter particles that went in and that went out. And this means that you are now back to square one, because to compute what kind of gravitational wave might be produced during this scattering, right, you really need to solve the nonlinear differential equations. Is this point clear?
If you observationally measure the
Yeah, then it's fine.
Formula you can
True.
predict the.
True. Yeah. If you can measure the full set of incoming momentum and full set of outgoing momentum over the whole solid angle, right, then indeed you can use this formula. Right? But from practical viewpoint, that's not that's not easy, right?
Simple case like a one particle ejected from one other. It's possible.
Yeah, but even if there is one particle ejected in this direction, gravitational waves propagate in all directions, right?
But this momentum is just then it was only that particle.
No, also the momentum of the gravitational waves. See, that's the point. That because you have to think of the gravitational wave as say massless particles that are going out, okay? And you have to include those in this calculation. Okay, so this formula has to be interpreted that way. That it includes sum over all final states.
Normally these sub theorems they are the series in Q. The graviton.
Yeah, that's in a soft graviton, right? But the finite energy gravitons, right, are what are called hard gravitons. They have to be included in the sum.
So your series is a 1/u series. It's not a Q series.
Well, it's related. I'll discuss this, right? I mean, it's a Fourier transform, right? You just go back and forth between the Fourier space and this space. But the important point is that even the soft graviton theorem, which I'm going to discuss later, when you apply it, right, if the sum over final states include the gravitons, the hard gravitons that are produced.
They are writing that in the time domain.
Yeah, this is in time domain. Yeah, this is written in the time domain. Okay. So this is somewhat inconvenient, right? Because how do you know what kind of gravitational waves are produced, right, without doing actual calculation? And indeed, for a mu nu, that's a memory term, there is no escape. Okay, you have to, if you want to compute a mu nu, you really have to compute what kind of gravitational waves are emitted during this process and put in this formula. And this is what is normally called the nonlinear memory term. It turns out that for the other coefficients, B mu nu and F mu nu, these are the tails, due to some miraculous cancellation, the contribution from massless final states can be expressed in terms of the massive state momentum. And I'll describe in the next slide exactly what you have to do. But the statement is that even if you don't know what kind of gravitational waves are emitted during this process, if you just knew what kind of massive particles went in and what kind of massive particles went out, that is enough to calculate these tail terms B mu nu and F mu nu. Is this statement clear? Even if you have, yes, it is true even if you have photons, indeed.
So by massive you mean hard particles, right? Photons could also emit like graviton.
Yes, so all those you don't need to know, right? What this is saying is that if we just knew what massive particles are there in the final state, that is good enough, right? If this process emits electromagnetic radiation or gravitational radiation, right, you don't need to know what kind of emission took place.
Gravitons coming out from the electromagnetic radiation, that is automatic.
That is also included in this. I mean, what this formula counts is the final state, right? Doesn't matter whether it's coming from through another photon or another massive particle, it doesn't matter, right? The final state is what matters, right? And what this statement is saying is that you don't need to know the final state gravitons or photons. Okay. Now in the next slide, I'll explain what exactly I mean by saying that you don't need to know. Yeah. If you have invisible massive final state, yeah, then you cannot apply this formula, indeed. Okay. In fact, the real use of this formula, as I say it, right, is not that you have to know all the particles and then you calculate the radiation, but it's more that if you observe the radiation, right, what can you say about what went in, right, and what went out? Because this gives a constraint on the kind of scattering that took place, right, which produced the particular radiation that you see. Okay, so let me show you this formula again, right? So this formula for A and B, right, includes this sum over final states, right? This unprimed momenta are the final state momenta. So here is a statement. Take the expression for B mu that we just saw. In this, there is a sum over final states. You simply drop all the massless particles or radiation contribution in the sum over final states. Okay, just remove them by hand. You just sum over only the massive final states. Okay, so the sum over A that you saw restrict to only the massive final states. And then you compensate by adding a term like this. So what is this term? So Pi, Pi is a total incoming momentum, right? Sum over all the P prime mu's. And Pf is a total outgoing momentum that is carried by only the massive particles. So if you knew what final state massive particles are being produced, you can calculate Pf, and then you can calculate this. So the statement is that in the expression for B mu nu, we can just restrict the sum over final states to only the massive particles, and then you add this extra term to this. Similarly, in F mu nu, we can restrict the sum over final states to only the massive particles, and then you add this extra term over here. Okay, so the Pf and Pi are the same that I have defined here. Now, what I want to emphasize here is that these formulae that I give here are not new formulae. These are just rewriting of the original formula. So here is an exercise. Take this formula over here. Okay, take the formula for B mu nu. Imagine that this final state has certain set of massive particles, certain set of massless particles. We now write a part of this which is sum over massive particle states, right? So where A and B are both referred to massive particles. And then there is the rest of the term, right? Where either A or B or both are massless. Separate those terms out, evaluate them explicitly, and show that those terms, right, add up to what I said you should add. This one. So this exercise you can do without knowing where this formula came from, right? This is a property of the formula. It doesn't matter how you got the formula, right? Take the formula that as given, and you can simply manipulate it to derive these two relations over here, this as well as this. Are there questions on this?
This is based on the conservation result.
No, I'm not using anything. We don't know why this formula works, right? We are simply saying that take the formula that are given here, take this formula, separate out the sum over states, final states, into massive particles, and then the rest. Right?
You are not using the fact that the sum of momenta is 0 of all particles incoming and outgoing.
Yeah, so that sum over P prime is equal to sum over P. That of course is true. Yeah, that we are using. Yeah. That of course you have to use, right? Sum over P is equal to sum over P prime.
That's all, not angular moment.
Yeah, not angular momentum, because angular momentum it doesn't even appear here. So the point is we don't know why it works, right? I mean, it's an observation based on the formula, but presumably there is a deeper reason why it works this way, right? Why is it that you can rewrite this complicated formula that I showed, right, in terms of only the massive final state momentum? So that's still an open problem, right? That what is the deeper understanding of why this kind of rewriting works, and it doesn't work for the memory term, right? As I said, it works only for the tail terms.
In those formulas, what is the information about the masslessness? You are not using the E square equal to 0 condition anywhere. So where
No, we are using, because in this formula you will see there is m's sitting here, right?
okay, that.
Yeah, so these m's will have to be set equal to 0, right? So that clearly that simplifies the formula. right? But the point is, it simplifies it so much that you can just, you don't need to know what those individual P's are. Right? You can have 100 gravitons emitted in different directions. Right? You don't need to know what directions they are emitted. Right? All you need to know is the total momentum that is carried away by those, right? Which is just the difference between the total incoming momentum and total outgoing momentum. Okay, I think something about explosion. Oh, the formula that I wrote down, I have assumed that the particles are neutral. Okay, that the particles don't carry any charge. If the particles do carry charge, then this formula will be modified. But the modification is known. I just didn't write down the formula because it will just make it more complicated. But there are formulae that exist even for charge incoming and outgoing particles, and those formulae are known. This is something that I have already said. I started by describing the example of an explosion. But explosion, of course, is just a special case of scattering, where the initial state has just one object. Right? One object breaking up into many instead of multiple objects coming together and going out as multiple objects. In this case, if you apply the same formula, you can show that C mu nu and G mu nu will vanish. These are the initial tails, right, which is physically clear why it should happen, because if the object is just sitting there, right, we don't expect it to start emitting radiation before the explosion takes place. Right? So the C mu nu and G mu nu will vanish, and E mu nu will take this form for large positive U. Okay, and these are again given by the same formula. Finally, I want to emphasize it again that these results are statements in classical theory of gravity. But they are easier to understand as classical limits of some results in quantum theory of gravity. Okay, at least initially, as I said, the tail terms are derived this way. They are not derived by doing direct classical analysis, but starting from a results in quantum theory of gravity and then taking their classical limit is how we arrived at this formula in the first place. So these results in quantum theory of gravity are known as the quantum soft graviton theorem. And this I have already said that their tail terms are first predicted from quantum soft graviton theorem, and then we now do have a fully classical derivation, right? Which is, I'll describe that explicitly. So this basically is the end of the statement of results, right? What kind of results is that we have at present. And now I'll focus on how we derive this. And in that analysis, I'll set from now on the speed of light equal to 1, right? Just to avoid having these factors of c floating around. Yeah, but I'll not set the Newton's constant to 1, at least not yet.
If you take the same thing in electromagnetism,
Yes.
you solve for A mu in a scattering in a soft theorem.
Yeah.
You will get certain terms, but not the tail term, because the electromagnetism, the photon does not produce a secondary photon.
But there will be tail terms because there will be charged particles in the final state, right? Those will produce tail terms. Yeah.
But there will be some difference in the gravity because
Yeah. The formula are different, so the formula exists in electromagnetism.
That part will not be there.
Exactly. Right. So certainly there are similar formulae in pure electromagnetism, right, for electromagnetic radiation, right, which are similar but not quite the same. Yeah, in fact, one particular feature, right, which is not the same in electromagnetism and gravity, let me emphasize. You see here that this is what happened in the past. C mu nu is the coefficient of the 1 over u piece in the past. Right? And this depends only on the momenta of the incoming particles. B mu nu and A mu nu are the coefficients of, these basically determine how the waveform looks in the future. But these depend not only on the future momenta, but also on the past momenta. Right? It knows about what came in, even though you are looking at it way after the peak of the waveform has passed you. It still depends on what actually went in, right? So what happened in the far past, and that is related to nonlinear effects of gravity. Right? In electromagnetism, what will happen is that the analog of A mu nu and B mu nu will depend on the future momenta, and this will depend on the past momenta. Pardon?
The massive visible part is enough.
Exactly, yeah. So what this is saying is that if we know the massive visible part, that's good enough to find a formula.
So then if you have neutrinos, you can still use it.
Yes, indeed. So you don't need to know the neutrino flux. Well, except the neutrons are not quite massless, but for this purpose, I think you can treat them as massless particles, indeed. So the neutrino flux will not, I mean, you can treat them exactly in the same way. Okay, so now I'm going to give the outline of the derivations. The details of the derivation, I think I'll try to postpone till next lecture. Okay, but I'll give an outline of both the derivation based on the soft graviton theorem and the derivation, the classical derivation, right? How do you go about proving such things? So this is the derivation based on soft graviton theorem. This is how we first arrived at those results on tail terms. So in quantum field theory, the scattering amplitude A gives the probability amplitude for transition of one state to another. Right? This is the standard meaning of probability amplitude. So in particular, mod A square is the transition probability from one state to another. Now suppose we know the scattering amplitude A for transition from some incoming state P to some outgoing state Q. Right? P could consist of a set of incoming particles and Q could consist of a set of outgoing particles. Okay? And there is a transition probability for any set of incoming and outgoing particles. There is a transition probability, and I call that A. So the corresponding amplitude I call A. Probability will be given by the mod A square. Now, soft graviton theorem is a result in quantum theory of gravity that gives us the transition amplitude for P going to Q plus some low energy gravitons in terms of the original transition amplitude A, which is for P going to Q. Gravitons are massless particles that represent quantum gravitational wave, just like photons are quantum electromagnetic wave. This result, the fact that you can get the result, the amplitude for P going to Q plus some low energy gravitons in terms of the amplitude for P going to Q, this is what is called the soft graviton theorem. You can prove this theorem based on general coordinate invariance. It doesn't have to be Einstein's theory, right? It can be Einstein's theory together with higher curvature terms, okay, as long as you maintain general coordinate invariance. And it doesn't even require a particular quantum theory of gravity, right? You can use string theory as an example, but if you have another quantum theory of gravity where the scattering amplitudes are well defined, this theorem will be valid. Okay, because this theorem really relies on the general coordinate invariance. But of course, it requires that the S matrix should exist, right? That should be a notion of scattering amplitude in the theory. Are there questions on this slide?
Typically, this requires Q mu of P mu is equal to 0. That is the statement of general covariance.
Yeah, that's basically a statement of general covariance. But the more technically, what one uses is that there is a one particle irreducible effective action that you can write down, right, which will have general coordinate invariance.
Yeah, but when you write in amplitude, momentum space.
Yeah, but you can convert to position. Yeah, so you can translate that general coordinate invariance into a statement on the momentum space representation, right? And that is basically, as you said, Q mu on the amplitude is equal to 0. Yes.
So is the soft graviton theorem going to give an approximation that will work as we send the momentum of the gravitons towards zero?
Yes, indeed, right? Low momentum, and under Fourier transform, the low momentum piece of the waveform will control the late and early time. Right? That's why the soft graviton theorem can be used to get results on the late and early time waveform, but not on the finite time waveform. Indeed. Other questions? Yes.
How
Yes.
many gravitons
We will see total energy carried by these gravitons will be small. Total energy carried by the gravitons, and we will see how many gravitons, that it will be fixed. I think in the next slide you will see the number of gravitons. But the theorem by itself, right, is valid as long as the total energy carried by the gravitons is small compared to the momenta that are carried by P and Q. Right, because you are really doing a Taylor series expansion in the momenta carried by all the gravitons. So this is a quantum result, but our goal is to extract some classical result out of it. Right? So you want to take what is called classical limit. So first of all, in order to take the classical limit, right, we take the external particles to be very heavy, highly energetic, large compared to the Planck mass. Classical objects have that property, right? A classical object like a planet, right? Imagine that you are throwing two planets towards each other, right? Each planet is much, much heavier than the Planck mass, right? So that's the limit that we are going to take. Let's take the states to be very massive objects, to consist of very massive objects. And then we look at the transition probability for P going to Q. Okay? These are the initial and the final states, plus M low energy gravitons. Okay? And let's consider each of these gravitons to have energy h bar omega and momentum which is in some direction h bar omega times n hat. This is stated in a somewhat loose way, right? Because of course, if you fix the exact energy and exact momentum, the transition probability is 0, right? You have to think of it being in some range, right? So when I say energy omega, I really mean the energy between omega and omega plus delta omega for some small interval. And when I say the momentum h bar omega n hat, I really mean that n hat is within some small solid angle. Okay, that's the kind of probability that we are trying to compute. And this can be computed using soft graviton theorem, because soft graviton theorem tells us how to calculate this in terms of the amplitude for P going to Q. And it turns out that this transition probability takes a form like this. There is factor R. R is essentially the P going to Q transition probability. S is what is called the soft factor. This is what is universal. This is determined by the soft graviton theorem. So for each soft graviton, you have a factor of S. If you have M low energy gravitons or M soft gravitons, then you get a factor of S to the M. And because the gravitons are bosons, they are identical particles, we have to divide by the symmetry factor, M factorial. This is a consequence of Bose statistics. So net upshot is that the soft graviton theorem tells us that if you want to compute the probability for P going to Q plus M low energy gravitons, that probability is given by a formula like this. In this formula, R is complicated because R basically requires calculating the transition probability for P going to Q, and P and Q are complicated objects, right? Because they are very highly massive external states, right? Maybe two planets, you are scattering two planets, right? So clearly that scattering amplitude you cannot use, you cannot calculate using any useful quantum field theory techniques. Okay? But S is the soft factor. Okay? This you can calculate using quantum field theory techniques, and this is known. Now let's look at this formula. Quantum mechanics tells us that you can't determine how many gravitons are produced. Right? It only tells you what is the probability of producing M gravitons. right? And that's this probability. But given this, you can now ask, what is the most likely number of gravitons that will be produced? And that requires maximizing this with respect to m. And if S is large, and indeed one can show, knowing the explicit form of the soft factor, that as long as the external states have large energy, S is large. So if S is large, then one can show using Starling's formula that this quantity has a sharp maximum at m equal to S. So this is saying that even though quantum mechanics allows for arbitrary number of gravitons to be produced, right? It doesn't fix how many gravitons will be produced, okay? But the probability of producing a certain number of gravitons is highly picked, and that is m, that is S. So you can say that the classical limit, in the classical limit, S is the expected classical number of low energy gravitons. Even though quantum mechanics allows us to produce arbitrary number of gravitons, the most of the probability is for a particular number of gravitons, and that is S. And if S gravitons are produced, and if each graviton carries energy h bar omega, then the energy that is carried by these gravitons is S h bar omega, right? And of course, all these gravitons emerge in the direction n hat, because they are carrying momentum omega times n hat. Is this logic clear? So this is the way one uses a quantum result results in quantum gravity, and takes the classical limit. Yes.
As you are mentioning, like two planets colliding and all, this R, if it's a elastic sort of collision, should be order 1, right? Because
no, R will be in fact very, very small, right? Because if we fix the initial and the final state, right? P and Q. Imagine that you say that you take two planets colliding, right? And look at a particular final state. Because the two planets go into some particular final state, right? That probability is extremely tiny, because there are so many possibilities, right? So R is a very, very small number, S is a large number, and this number is still a small number, right? R S to the M is still a small number, but that's not very important for us, right? Because all that is important is that this should be smaller than 1, right? The total probability, of course, cannot be larger than 1. Okay? So even though S is large, you compensate by having R very, very small. Yeah. Okay. What is? N hat is, so I looked at gravitons that carry energy h bar omega and a momentum h bar omega n hat. Right? From the classical perspective, n hat is basically the direction in which the gravitons are coming. Right? Because the graviton is carrying momentum h bar omega times n hat. N hat is some unit vector. Okay? So that's the direction cosine of the detector. Right? Because those gravitons will reach the detector at an angle n hat. S is a function of n hat, yes, indeed. S is a function of n hat and omega, right? Because it knows about the gravitons. Yeah, it's a universal factor function, but it depends on both the data on the graviton energy and momentum, and also the external momentum of the P and Q. Polarization of the graviton. Yeah, so I should have said that also, that this can be calculated, each of energy h bar omega and momentum h bar omega n hat, and also some particular polarization. Okay? So you can calculate this number for all the two different physical polarizations explicitly. The S is
Some finite number.
Yeah, S is a finite number. S is a finite number that can be calculated, right? Quantum soft graviton theorem tells us what S is, right?
I'm just trying to understand which one is the classical.
Oh, the classical limit required that we take P and Q to be very large energy, right?
But does it mean that the A equals to S for large is also?
Yeah, so in that limit, S becomes large. The formula for S depends on the momentum that P and Q carry, right? And in that limit, S becomes large, right? It's only when S becomes large that this is a sharp function, right? For a S of order 1, right? This number is not sharply peaked, right? It's some distribution in M. But when S becomes very large, right? Imagine S is a million, right? Then you can easily check that this is sharply peaked around M of order million. And you basically have to take the log of this and take the second derivative, right? To see that it's a sharply peaked function. Any other question? So once we have determined the number of particles, energy carried by these gravitons, we can calculate a classical flux of energy carried by this gravitational wave of frequency omega, and that's obtained by simply multiplying the number by the energy carried by each graviton. And here, as I just pointed out, I should have also mentioned that this can be done for each of the polarizations separately, right? So this S will depend on the particular polarization. So if you can take two different polarizations of the graviton, and S can be calculated separately for each polarization. So once you have the energy flux, right, we can now translate this into the time Fourier transform of the gravitational waveform. Okay, because if you know what the gravitational waveform is, you can write an expression for the energy flux in terms of the gravitational waveform, okay, and you can reverse this. Right? If you know what the energy flux is from this quantum calculation, you can reconstruct the gravitational waveform from there. So this is a Fourier transform of the gravitational waveform, and then you simply have to take the inverse Fourier transform to get the late and early time profile, and that leads to the results that I described. And the reason that we can get information only about late and early time is because we can get this result on this energy flux only for low energy. Right? Because soft graviton theorem really requires going low in energy, okay, and that's what restricts you to focus on the late and early time profiles. Are there questions?
What do you call classical? Can you go back to your?
Yeah.
So you are calling something classical by maximizing the number.
Yes. So the classical limit is when we took by taking P and Q to have consist of particles, each of which has large momentum.
Yeah, so you want large number n.
Yes. So given that, right, then we take M to be arbitrary number, right, and this is the formula for the soft graviton theorem. Now we ask for what value of M is this maximized. Okay. What you find is that as soon as you take the energies of particles in P and Q to be large, this factor S becomes large. Okay. So now you have a function here, right? R is a constant. S is a large number. You ask as a function of M where it is peaked, right? And you find that it is peaked at M equal to S, right? And the peak is sharp, right? That's the classical limit. So this is saying that as soon as you take the external particles to have a very, very large energy, right, the number of gravitons that is emitted, right, even though it's quantum, quantum mechanics doesn't fix exactly how many number of gravitons will be emitted, but the probability of emitting a particular number of gravitons is sharply peaked.
The question was that normally when you call something classical, you count across powers.
No, this is not the way we are counting here.
So this final energy is S H cross.
Yes.
It should be 1 by H cross. In the
S has an 1 over H bar.
So it does cancel.
It cancel, yes, of course. Right? Because the formula that I showed earlier didn't have any H bar, right? And this one also doesn't have.
So S should have 1 by H bar.
S has 1 over H bar. Yeah. So if you look at the soft graviton theorem, right, S has an 1 over H bar in that formula.
In that sense, that energy is independent of H bar.
Exactly. Energy flux is independent of H bar. Yeah, otherwise you couldn't interpret this as a classical formula. Yes. The total energy that is carried by the soft gravitons should be smaller than the total energy that is coming in, indeed. All possible? Yes, indeed. Yeah, that's true. Yeah. Right? So the total the idea is total energy that is emitted in the soft gravitons, right, all n hat integrated, should be small compared to the total energy that is coming in, indeed. Right? And that can be checked self-consistently. That in this classical limit, right? Classical limit in this case means that the external energy is very, very large. Okay? Total amount of energy that is radiated in the soft factor indeed remains small. Now, this logic that I described works straightforwardly in dimensions larger than 4. But in 4 dimensions, that turns out to be extra subtleties. And the subtleties have all to do with the infrared divergence. It turns out that in 4 dimensions, the soft factor is infrared divergent. And so you need to regulate the infrared divergence, right? So you have to go back and check your quantum soft theorem again, right, to see what do the infrared divergences mean. No, just soft divergence. Soft divergence in the amplitude. Not because in gravity you don't really have collinear divergence. Okay? It's the soft divergence that is affecting.
Denominator, that P dot Q, the soft theorem.
Yeah, that is collinear, but that's not a divergence. No, that does. Yeah, because the solid angle integral just kills it. Right? That divergence is not present in the final formula. Right? Is the soft when all components of momentum become small. Right? Those are the regions that give the divergence. So this is the first problem, that the infrared divergence has to be regulated. The second issue is that because the analysis proceeds by computation of the energy flux in different frequencies, it's insensitive to the frequency dependent phase of the waveform. Right? The energy flux is really the mod square of the amplitude. Right? So it doesn't determine explicitly the phase of the amplitude. Right? You have to do a little more work to figure out what the phase is. In any case, these can be solved, right? And indeed these were solved to figure out what the soft factor really is, okay, and how to extract the tail terms. Okay. But as I said, these are extra complications that one has to deal with in d equal to 4. For d larger than 4, this procedure gives you the result on the dot without doing any modification of the soft theorem. So I'm going to describe now an outline of the direct classical analysis, okay, and most of tomorrow's lecture will be focused on this. Okay, how do we go about doing a direct classical analysis? And this doesn't have the shortcomings, right? Classical analysis is straightforward. No, we are not using the super translation at all here, right? This is purely a quantum amplitude, okay? And the quantum amplitudes have infrared divergence. And in both in quantum electrodynamics as well as in gravity, we know how to deal with the infrared divergences. Right? So that's all we are using here.
So you said it works in other dimensions?
It works in other dimensions and all the subtleties are not absent. Right? You can get the waveform, okay, without any issue about infrared divergence. In 4 dimensions, you have to do a little more work because soft theorems themselves get modified. Right, in 4 dimensions. Once you start taking into account the effect of loops, the soft theorem in 4 dimensions is no longer the Weinberg soft theorem. Right, so those you have to take into account. And that tells you what also addresses these infrared divergence issues.
And these divergences are regulated, like you just drop the 1 by epsilon term? Or
basically, what you find in the explicit amplitude analysis, that the divergences are effectively regulated by the frequency itself. That the internal loop momentum divergences, right, are regulated by the external frequency of the external gravitons. So at the end, these divergences are not there, right? The final result is independent, doesn't have these divergences. Naively, if you try to use the classical, use the standard soft theorem, you run into these divergences. Okay? But if you do things carefully, right, you find that the divergences are automatically cut off by this omega inverse. Okay, so now in the next few minutes, that I have left, I will describe an outline of the direct classical derivation. Right? But as I said, in the next lecture will be mainly focused on this. So what is our goal? We want to find H mu nu or equivalently E mu nu that is generated during a collision process. So we just proceed as we will do in normal classical mechanics. We write down the differential equation that determines H mu nu or E mu nu. And because gravity is a gauge theory, you have to gauge fix. So we use say de Donders gauge and write the Einstein's equation. And here I have written the Einstein's equation. This is highly deceptive because this looks like a linear equation, right? The catch is that all the nonlinearities of gravity have gone onto the left hand, or to the right hand side. Okay, because I have not told you what T mu nu is. Okay. So the idea is you take Einstein's equation, right, identify the linear part of the Einstein's equation, right, which in the de Donders gauge is just box C mu nu. The nonlinear part of R mu nu minus half R G mu nu, you all bring to the right hand side and call that part of T mu nu. Okay, so T mu nu has complicated dependence on the gravitational field itself. Is this clear? So it is just rewriting of Einstein's equation. I have not really done anything, right? All the nonlinearities are hidden because the right hand side depends on quadratic, has quadratic and cubic and higher order terms in E mu nu. So this is what I have said, the T mu nu on the right hand side depends on E in a non-trivial way. The particle trajectories, right, also enter T mu nu, but they depend on E mu nu, right, because the gravitational field affects the particle trajectories. So this gives a complicated nonlinear partial differential equations that we have to solve. And these nonlinear partial differential equations may not even be known because the interactions are typically unknown. Because I said that there can be nuclear explosion in the middle, right, which we don't know how to describe in general. So at this stage, it's a completely formal equation. Okay, but let's go ahead and see how we can make sense of it. And I should say that this box over here is the Laplacian in flat metric. Okay, all nonlinearities, right, that can come from the part of the Laplacian because you have to evaluate in curve metric. That is on the right hand side. So we are going to work with this time Fourier transform. Okay, so we take E tilde mu nu, we define this as the time Fourier transform of E mu nu, okay, and this is just an extra phase that I have included in the definition of E tilde, right? Because one should really use the retarded time, which is T minus mod x, okay, but I have just written it as an external phase. So this is the definition of E tilde mu nu. And now the idea is that we are looking for E mu nu, okay, the part of E mu nu which goes as constant for large U, right? And by taking the Fourier transform of what a constant for large U corresponds to, one can show that this corresponds to E tilde mu nu going as omega inverse. Okay. See, it's constant for large positive U, but 0 for large negative U, right? That's what matters. And if you want to know what kind of E tilde mu nu comes out of that, it's omega inverse. Right? This is a straightforward exercise. You can check that if you have a function that goes to a constant for large positive U and 0 for large negative U, the corresponding Fourier transform will go as omega inverse. Similarly, if you want to get a E mu nu, which is of order 1 over U, then this will correspond to E tilde mu nu going as log omega. And E mu nu of order log U over U square corresponds to E tilde mu nu going as omega log omega square. So if you are looking for, if you are using this variable, E tilde mu nu, then what you should look for getting the results that we quoted are the coefficients of omega inverse, log omega and omega log omega square in the E tilde mu nu variable. And one feature that is common between all of these is that these are non-analytic at omega equal to 0. Now, what do you mean of non-analytic? Right? Non-analytic doesn't mean necessarily that divergent at omega equal to 0. Right? In fact, you can see that these of course diverge at omega equal to 0, but this doesn't. Right? The omega goes to 0 limit of this is perfectly fine. Right? It's a 0. But non-analytic means that if you take sufficient, my time is up already. Okay, I'll just finish in 5 minutes. That if you take sufficiently large number of derivatives with respect to omega, then it will eventually diverge. Right? And indeed that happens. Right? This doesn't diverge, but imagine that you take the first derivative with respect to omega, right? You get a term proportion log omega squared, and that will diverge as omega goes to 0. Right? So that's the meaning of non-analyticity. The derivative, sufficiently large number of derivatives with respect to omega will diverge. So now we go back to this equation, right? This is flat space Laplacian. We are trying to solve this. Now, of course, we cannot solve this because T mu nu has dependence on E. Right? But we can formally solve this, right? We can formally solve this by simply writing E mu nu as the retarded Green's function times T mu nu integrated over y. That's what the retarded Green's function is supposed to do. This is retarded Green's function in flat space time. Now you can write a Fourier transform version of this because you want to write in terms of E tilde mu nu. And one can show, and maybe if I have time, not today, but next time when I am doing this in detail, right, I will show this, that one can show that this equation for Fourier transform and for large R or large mod X takes this form. Okay, this is just the ordinary Fourier transform of T mu nu. Again, this doesn't solve anything because T mu nu itself depends on E. Okay, it's just a rewriting of the original equation. So now let me give the punchline as to why we can get anything useful out of this analysis, right? Because so far you have not really done anything except by rewriting the Einstein's equation. So we have this equation, right? This is exactly the same equation that we wrote here. So now suppose we divide this integration region into two parts. One is what we call the scattering region, where all the complicated things are happening, right? Where the particles may be fusing, splitting, having non-trivial interactions. Okay? That's all happening inside some finite region S. And then you have the asymptotic region that is called the complement of S in space-time. And this integral over d4y can be divided into the integration from inside S and the integration from outside S. Now, you see that the non-analytic terms in E tilde mu nu cannot come from the integral of a finite quantity over a finite region. So let's look at this. What do you mean by non-analytic terms? That if you take sufficiently high number of derivatives with respect to omega and then set omega equal to 0, you should get a divergent result. Now take the derivative with respect to omega of this side. Right? Omega appears inside k, right? So you'll keep bringing down factors of y, right? The coordinate. But as long as the y integral is restricted to a finite region, however many powers of y you bring down, this integral will always give a finite result, even for omega equal to 0. So the integration over this region cannot produce non-analytic terms. And the kind of terms that we are looking for are non-analytic in omega, at omega equal to 0. So this shows that those terms will have to come from the region outside S. Okay, the region inside S, where all the complications are happening, cannot contribute to the terms that we are looking for. So this is the main idea now, that we restrict, then this y integral can be restricted to region outside S. In this region only long range forces are important, and furthermore in this region the gravitational field is small, so T mu nu also simplifies, and in fact we can do an iterative procedure to solve these equations. This doesn't mean that we can ignore the nonlinearities, right? but we can systematically take into account nonlinearities by solving these equations iteratively. And that's what essentially leads to the results that we quoted earlier. So next time we will do the first two iterations and we will see how we can recover the expressions for A and B. Okay. The expression for the F and G I will not even attempt because that's the next iteration, right? It is just much too complicated to discuss in a lecture. But I think I'll try to give an overall idea of how this iterative procedure works next time. So I think today I'll stop here. Yes.
Can this be applied to black hole mergers?
Yes, it can be. If you take binary black hole merger, right, then it's like one body going into basically one going to 1 plus massless states, right? That's somewhat trivial in this case, and the result that one finds is that the 1 over u coefficient and 1 over u square log u coefficient does vanish in that case, right? So that's a, you can say, negative result, right? It's saying that you don't have a 1 over u tail, but it can still be tested that in the gravitational wave profile at that time you shouldn't get this 1 over u or 1 over u square log u terms. If you have two bodies, right, bound together, you can just think of it as one object. Right? The binary system, you just think of one object which goes into one final black hole and all the gravitational waves. Right? And then you use this replacement formula that I showed you, that we may not know what kind of gravitational waves are produced, but we just use these formulae. Right? That we can forget about what gravitational wave was produced, right? But rewrite this in terms of the total final set momentum. Right? And using that, one finds that the B and F actually vanish at the end. Right? And that's what shows that there is no 1 over u or 1 over u square log u tail in that case. But if you have two black holes colliding, right? Two black holes coming from infinity and colliding and say merging into a single one, then there will be 1 over u tail. Right? Because now it's 2 going to 1, not 1 going to 1.
Any other?
How can I compare your results with, for example, post-Minkowskian
Yeah, see, the post-Minkowskian type calculation is in a different regime because that's telling us what happens in before the merger has taken place, right? Whereas this is giving us what happens at late time, after the quasi-normal modes have died, right? What kind of waveform you expect. So I think you cannot compare it directly because they are really working in different regimes.
Ring down predictions are the same. Nothing.
Yeah, ring down prediction, of course, you are not even making a prediction because ring down prediction you cannot make using this, right? What this is saying is what happens way after we ring down, right? That the signal, there will be a memory term, but what it is saying is that if you have this binary merger, then there will be only the memory term, but no other tail, right? At least no 1 over u or 1 over u square log u tail. There will be higher order tails, right? That we don't know whether they exist or not. That's one of the things we are working on now, right? I mean, we believe that it is possible to write down an explicit formula for 1 over u to the n log u to the n minus 1. Okay? It's just we don't have the formula yet, right? It will be much bigger, yeah. So there will be an algebraic algorithm. The point is we have written a similar formula for electromagnetism. So 1 over u to the n log u to the n minus 1, that you can explicitly write down an algorithm to find the corresponding coefficient. And anything that can be done in electromagnetism, our experience is it can also be done in gravity, except that it's more complicated. Right? So we believe that those coefficients are universal. And one of the things that we want to test, of course, is that if you have a binary black hole merger, right, it's like 1 going to 1 plus many gravitons, then whether those tails are present or not.
Other questions? Yeah.
So
Minkowski and type cognition, I remember there are many polio terms and hypergeometric cognitions. But
Yes.
in your result, such terms don't appear.
Yeah.
Any reason for that? I expected polio.
Yeah, I think the point is because these are universal results, right? It doesn't. These are because they're universal results. These don't depend on what kind of particles went in and what kind of particles are produced. Right? So universality basically, I think, precludes having complicated functions. Right? I mean, these are only algebraic functions that we get at the end. Whereas post-Minkowskian, it is true that you get complicated functions, but that's a very specific binary black hole system. Right? If you had 3 objects instead of 2, or black hole neutron star, results will be different. Right? Because neutron star will have tidal effects, for example. So any universal factor is likely to be simple. Right? That's my guess. That's the reason why we don't have complicated functions here.
Okay, so thank you.
This depends upon having asymptotic free states and then they interact. But is that right?
Yeah, that's right.
But if you have a binary which is just merging, so it's.
Yeah, then you can just think of this as one object.
It's only one guy.
One object, right? Then initial state, of course, it's never a free object, but final state is still a set of particles, right, which are going out. And so final state waveform you can predict based on this. Right? So that's why the binary black hole merger, if you have that system, how the waveform looks in the final stage, you can predict using this. Right? Is that to the extent that you have calculated the 1 over u and 1 over u square log u, those coefficients are 0 in that case.
And this last proof that you said that your non-analytical part doesn't come from the bounded region.
Yes.
That is based on the fact that your T mu nu doesn't have non-analytical in the frequency space.
That is finite. The T mu nu is finite.
So you are assuming that, I mean.
Yeah, because I mean, in any physical situation, right, we don't expect infinite T mu nu. And these are all outside horizon. See, anything that is happening inside the horizon, of course, has no effect on the asymptotic radiation. Right? So outside the horizon, we expect T mu nu to be finite.
Yeah.
I have some questions about the phenomenological implications.
Okay.
Some questions about the phenomenological implications of the gravitational wave memory. So for one thing, did I notice correctly that the formula for A mu nu has a 1 over r factor in it? So
yes,
memory is weaker further from the source than close by to the source?
That's true, yes.
So am I imagining that most of the sources of gravitational wave memory in the universe today are binary black hole mergers, is that a reasonable expectation?
Yeah, probably, at least in some frequency range, yes.
So, and they're localized within galaxies. So am I supposed to be picturing that nearby to a galaxy, suppose I have an old galaxy where there have been many binary black hole mergers occurred. Nearby to that galaxy, I've accumulated more memory, whereas in the voids between galaxies, I have a smaller amount of memory. Is that the right way of thinking?
That is true, but also the point is, if you are averaging over many such processes, right, then the memory is also directional. This A mu nu is a tensor, right? So there will be cancellations because different mergers will have different directions.
So then they would sum like a random walk, presumably. Where
That's right,
I would accumulate,
exactly.
but at a root n rate, at a root number of mergers type rate, rather than just with a number.
Exactly, yeah. Or you can look at the correlation function. The memory is at here with memory at somewhere else, right? The 2-point function, for example, will get a non-trivial result, okay, even after averaging.
So one could derive a prediction for, I guess, how much memory there is as a function of distance away from an old galaxy, and is that a potentially measurable quantity?
I think so, yes. I mean, if you do a statistical analysis, right, it should be measurable. How much average memory you expect, right? Which, as I said, you should have a square root of n factor. But there is the tail sometimes can dominate the memory, right? The tail effect. The bullet cluster, for example, right, when things are just passing through each other without really deflecting very much, the memory term vanishes, right? But the tail is non-zero, even in that case, right? Because tail survives even when the particles don't scatter. Okay? So as I said, for bullet cluster, if you actually calculate the the tail term, it's of the order of, the strain is like 10 to the minus 14, which is way above what LIGO has detected, right? It's 10 to the 7 times the LIGO result, except that it's very slow. I mean, it's changing very slowly. Okay? But there may be some average tail effects that may be more observable, because in our universe, for example, black hole mergers are happening once in a while. But if you think of this as a gas of particles that are moving around, right? You imagine each galaxy is like a molecule, right? They're all moving around. Maybe not scattering very much, but each such movement produces a tail effect, right? Because the galaxy, they are just passing. For each pair, there will be some tail effects of this kind, and that may have more significance than what you get by averaging memory from the black hole merger. But again, on the average, it will be 0, so there will be the square root of n effect that you have to look for.
Okay, so are there other questions? Okay, so if not, let's thank Ashok for the excellent talk.